Search for Nikola Tesla today, and you will find a figure defined by supernatural claims, a man who communicated with Mars, built earthquake machines, and extracted energy from space. The historical Tesla was a pragmatic physicist and electrical engineer who relied on the constraints of the laboratory to prove his theories. These myths center on his 1899 experiments in Colorado, where he supposedly conjured 12 million volts of electricity and hurled 65-foot artificial lightning bolts across the plains. These accounts often ignore the reality of his methodology. Tesla was a methodical researcher who designed his hardware to test specific mathematical boundaries and recorded every outcome with engineering precision. We know his exact process because he documented it. His Colorado Springs notes serve as a day-by-day investigative log, providing an empirical record of his most extreme high-voltage tests. Inside these journals, he logged precise metrics for every test, tracking input voltages, oscillation frequencies, and the capacitance required to keep his equipment from failing. Analyzing the documented hardware and the physics found in these pages is the only way to understand his actual engineering achievements. In New York, Tesla's electrical resonance work had hit a physical limit. The density of the city made it impossible to scale his experiments to higher power levels. A laboratory fire in 1895 destroyed much of his custom-built equipment, forcing him to spend years planning a facility that could handle the stresses of high-potential currents. In 1899, he moved to Colorado Springs, establishing a facility in the open environment needed to test his high-frequency oscillations on an industrial scale. This new laboratory was designed for one primary purpose: to safely increase the production of high-frequency, high-potential electrical energy. Tesla utilized massive sparks jumping across air gaps to observe how the system responded to extreme electrical pressure. To succeed, he had to handle pressures in the millions of volts without melting the copper conductors or destroying the very coils generating the current. Tesla constructed the Colorado Springs facility as a specialized industrial laboratory, designed to push 19th-century materials to their absolute physical limits. The engine driving these experiments was a technology Tesla refined specifically for high-power testing: the electrical oscillator. This device was a massive LC circuit, a system that coordinates an inductor coil and a capacitor to store and release energy. This diagram shows the foundational architecture of the circuit, where a capacitor is linked in a continuous loop to a primary inductor coil. During the charging phase, electrical energy builds up inside the capacitor until it reaches its maximum capacity. In the discharge phase, the capacitor dumps its entire energy load into the primary coil in a fraction of a second. This rapid cycle creates a quivering current, inducing massive voltage spikes in a secondary, larger coil positioned nearby. Data from his Colorado notes confirm the system reached extreme rates of vibration, recording up to 130,000 alternations per second. By magnifying the immense electrical pressure through this exact method, Tesla achieved unprecedented tensions exceeding 12 million volts. The magnifying transmitter functioned as an incredibly scaled-up, meticulously engineered resonant transformer. High voltage is difficult to control. To transfer energy without destroying itself, every component had to be tuned to a specific frequency. Tesla explained this through a mechanical analogy, striking one tuning fork to make a second distant fork vibrate. Energy moves seamlessly between two objects only if they share the exact same resonant frequency. In his high-voltage circuit, the vertical transmitting wire acted as that first tuning fork. His notes revealed the mathematical rule for resonance. The system's success depended on the exact physical length of the wire. He determined the wire length must equal exactly 1/4 of the electrical wavelength to establish a standing wave within the circuit. Following this rule allowed him to control immense power with minimal energy loss, keeping the current contained within the hardware. This mastery of resonant frequencies defines the engineering logic required for wireless transmission, regardless of whether the energy moves through the air or the earth. Despite modern comparisons to radio, Tesla was not attempting to broadcast power through the atmosphere. He explicitly rejected Heinrich Hertz's model of airborne radiation, viewing the air as too much of an insulator for moving large amounts of energy. His alternative theory treated the Earth as a giant conductive reservoir and electricity as an incompressible fluid that could be disturbed. This schematic contrasts the two models. On the left, the standard airborne model radiates energy away from the source. On the right, Tesla's model forces the energy directly into the planet, minimizing airborne radiation and maximizing current pushed into the soil. In Colorado, he connected the base of his oscillator to a heavy copper plate driven deep into the ground. By pumping 12 million-volt pulses into this connection, he intended to vibrate the Earth's own electrical charge at a resonant frequency. Tesla's engineering goal centered on turning the entire planet into a single conductive wire for his circuit through resonant ground conduction. When these electrical pulses move through the Earth's crust, they eventually hit the opposite boundary of the globe. Like a sound wave creating an echo off a wall, these electrical waves reflect and bounce back toward the transmitter. This simulation shows the outgoing pulses meeting the returning reflections. When they collide at the correct frequency, they lock into a stable, repeating pattern. Tesla recorded this specific phenomenon as a stationary wave, claiming his instruments detected these reflections returning through the ground from thousands of miles away. If the planet could maintain these stationary waves, a receiver tuned to the same frequency anywhere on Earth could connect to the ground and draw power. This theoretical global wireless power grid relied entirely on the planet's ability to act as a low-loss resonant medium. The Colorado data convinced Tesla to move back to New York and secure funding for a commercial-scale global transmitter. The Wardenclyffe Tower project became the final physical test of his stationary wave theory. However, the project revealed a critical flaw. His mathematical model failed to account for the immense energy loss that occurs when current moves through the Earth's diverse geological layers. While his local circuits operated perfectly, the Earth was not the perfect, lossless conductor his global plan required. Although the global power grid remained a theory, the high-frequency oscillators and the strict tuning laws he perfected provided the technical requirements for the first successful wireless communication systems. The rigorous mastery of high-voltage engineering and resonant circuits documented at Colorado Springs defines Tesla's actual legacy, providing the technical blueprint for the modern connected world.